Okay, thank you so much for joining us today for this webinar. We're going to talk about continuous optimization of compiler flags. And with me today is Steve Wallach. I'm so happy you can join Steve. Steve is a serial entrepreneur, has founded several companies in the HPC space. And also with us today is Tomer Paz, Consortio's VP of Product. So what we're going to go over today is, first of all, the basics of compiler flag mining, what it means, what it's good for. Then we're going to start speaking a bit about automation. So first we'll talk about how to statically optimize with Consortio's product Optimizer Studio. Then we're going to talk about how to implement continuous optimization of compiler flags and some best practices. And of course, we're going to do a live demo and a short walkthrough to explain how to get this working. So first, I'd like to start with you, Steve. Thank you so much for joining in this webinar. Why don't you start with telling us a bit about Convex and about your experience?
Okay, thank you very much. Yeah, I was the technical co-founder of Convex. We started in 1982, and our product was, as I call it, the mini computer version of a Cray program like a VAX. And at that time, it was difficult compiler technology to do automatic vectorization and parallelization. And we were fortunate enough to work with Ken Kennedy at Rice University and his students. So we built a compiler ground up that automatically, over the years, vectorized and parallelized Fortran C. And we also did interprocedural analysis. And even by today's standard, it's very advanced. And as a technical co-founder, I got involved with key benchmarks and working with competition. And in some cases, with our compiler team, whenever something wasn't clear, they would put a flag. And the reason you wanted a flag is to have portability of application. And other vendors did the same thing. And at some point, I coined the term switch envy. I created a presentation to say that to get performance, you had to understand how tens, if not hundreds of flags interacted with each other. And that's unacceptable over the long term. Combination of portability of code. In many cases, you have to understand computer architecture to know which flags to use if they talk about cache sizes, instruction sets, etc. So when I became aware of Consortio's applications and what they do, I go, wow. I consider that a major advance in tuning, because in many cases, the user doesn't really tune the code. We used to have 15, 20 people doing nothing but tuning application code, knowing about switches. And in many cases, we could not change the source code because they wanted portability. So having an integrated environment that's scalable over time is a major advance as people like myself continue computer architecture designs with innovative instructions and other techniques.
So can you, that's great. Can you maybe explain a little bit more what compiler flag mining means?
What compiler flag mining means is there are certain flags that are unique to a particular implementation. If you advance that slide a little bit, animated. There are flags that say how you handle delay slots or how you handle floating point. And unfortunately, every implementation, those flags can mean different things. So it's like you tune for release 5 of a design and release 6 comes along and it may not be the same flags that work for optimization. And one can argue that compiler people should generate source code for all these releases, and at runtime, you select which is the right version. And that can be done for certain things. But in the long run, there has to be a better feedback between flags where you shouldn't need a PhD in computer design to understand how to tune for a flag. And one of my views is the machine which is simplest to program will win. User cycles are as important as CPU cycles. So optimizing user cycles, I think going forward is as important as optimizing user cycles.
But how many flags really have you had to deal with?
Too many. And at Convex, I actually wrote a cookbook of how to optimize and tune codes, where it was 5 or 6 pages. Each page had 15 to 20 flags. And I would create a flow chart of, if this is what happened, first try this, then try that. And it's a very iterative process. And that, way back when, it was all manual. And it takes a lot of effort. And again, we had to train people. And generally, the users weren't interested in this. They tried simple things. They were just interested in dash 00, 01, 02, 03, etc. And when you start trying to compile with 7 or 8 different flags, it becomes very difficult to maintain and understand what you're doing.
But was it worth it going to, I mean, what's the potential? Why wouldn't I just use -02?
That's a great question. And the reason we did all this, because in some cases we could get 2x the performance for the same hardware cost. And, you know, and even getting 25, 30% performance was worth the effort. So, and that just shows you the sensitivity of computer performance relative to compiler optimizations. It's not just running a clock faster or having more cores, but tuning a particular uniprocessor performance. And it also shows you how sensitive performance is to the underlying computer architecture because of inherent parallelism in the hardware, etc.
Okay, great. Let's continue from this point. Thank you, Steve. Please stay on. So now we're going to talk a little bit about, static optimization in the general sense. So if we look at a system today, at the computing system, it has a lot of tunables. You can find them in the processors. For example, in Intel processors, you can toggle the last level cache prefetchers. You have tunables in the firmware, in the operating system. You have many in the middleware, the applications, and of course, even the choice of compiler flags that you use to compile and build your binary. The idea is that if you tailor all of these settings to whatever you're running, you get significantly higher performance and lower costs. Now, it used to be easy when there were only a handful, but now, these days, we are already in the hundreds of settings. Just compilers have hundreds of flags, and it's becoming very, very difficult. And obviously, you cannot go and run an exhaustive search on all the possibilities because the number of possibilities is simply enormous. And doing things manually has a lot of challenges. First of all, not a lot of people know how to do this because you need to be an expert in many domains. Steve, you mentioned that you had to really be an expert and understand computer architecture to choose the right flag. So it immediately narrows it down to a very small group of individuals around the world that can actually do this in a good way. It's also expensive in the sense that every time you change the hardware or you change the software, you have to retune. It's like a moving target. And it's also ineffective in the sense that we know that computer programs have different phases of execution, and each phase may require different settings. But when doing things manually and statically, you basically use the same settings for all the phases together, so you are actually optimizing for the average phase. So for these reasons and others, we see that most systems today are not optimized for their workloads, and this is where there is a big opportunity. So let's talk a bit about what static optimization means before we go and discuss automation. So let's say you have some kind of workload that you'd like to optimize. So you prepare your workload, maybe you wrap it in some kind of script. After that, you choose your optimization target. So In our case, we're going to use compiler flags to improve the performance, and it can be some kind of score that the benchmark outputs, and you want to maximize the score, or maybe you want to minimize the runtime of your program. Then you define what your tunable settings are. So in our case, in this webinar, we're going to look at the compiler flags that are used to build the program, but you can also look at other types of tunables in the system, as I mentioned before, from hardware to software, all of these settings. Then starts the actual tuning process where you select some kind of system configuration. In our case, we choose some compiler flags, and then we build and run the program and measure the result. And we do this iteratively, and we keep searching the parameter space until we find something that we are comfortable with, or we run out of time, and then we report the results. So this is more or less the flow of how a performance engineer would tune a workload. Now, how do we automate this? So Concertio's Optimizer Studio basically automates this iterative part of selecting a system configuration, running and measuring. The idea here is to use an advanced algorithm that can search the huge parameter space. And we use a genetic-based algorithm. Another thing that needs to be taken into account is that systems have variability. So I will demo that later, but when you run a program several times and you measure performance, every time you run it, you get a slightly different result, and you have to deal with that somehow. So Optimizer Studio has several mechanisms to deal with variability. So it increases the confidence in the result, and also the reporting part. But basically using a tool to do this kind of work basically standardizes the optimization workflow in a scientific way. In terms of defining the tunables, so what Optimizer Studio offers is a library of tunables. For example, you're optimizing GCC flags. So with one directive in the configuration file, you just import all the flags, so you don't have to search for them. Or you want to optimize the Linux tunables, all the tunables in Linux. And I will show you that in the next slide. In terms of the optimization target, so you can choose something simple, like minimize runtime or maximize the score, but you can also choose something that is multi-objective, like I want to maximize the network bandwidth while minimizing while having the latency not exceed a certain threshold of like 100 milliseconds. So you can have these kinds of complex functions. And of course, when preparing the workload, so we have best practices to help users. The idea is that compared with manual tuning, doing things in an automated way allows you to achieve greater speedups because the algorithm can find better configurations than manual tuning. It's done quicker because the algorithm knows how to search quicker, and with much less effort. You keep it running, you run it, you come in the next day and you have the result. It runs overnight, so you don't have to do the iterative process. Here's a library, a partial list of the tunables that are supported by Optimizer Studio. If we start on the bottom, we support GCC flags, and more compilers are coming soon. But you can see here the full stack from processors to OS, orchestration tools, OpenMPI, a bunch of databases, runtimes like Java, web servers where we see great results, and networking gear of Mellanox. So I'd like to set some definitions straight and to talk a little bit about the techniques that are supported by Optimizer. So I mentioned a bit about static optimization. What that means is that you have some experiment in the lab, you run it. The output of this experiment is a set of recommended settings, and then you go to the production environment and you apply these settings. And this is why we call it static optimization, because the recommendations are static. Next, continuous optimization. So continuous optimization means that you integrate static optimization within the CI flow or the continuous integration flow or continuous delivery flow. And the idea is that you run static optimization in an automated way. So in this webinar, we are talking about integrating into the continuous integration. We have commit, build, test, and before you deploy, you run another step called optimization, continuous optimization. And here you try to mine the compiler flags and recommend the best ones, and only after that you deploy. The third technique that I want to talk about is dynamic optimization. This means that all of the optimization is done automatically and in real time on production systems. So the first step is you deploy an agent in production, and then you wait a few minutes while the agent learns what is going on. And then after a few minutes, you will start to see the optimization in real time, and the performance simply improves on the end device. So this is supported by our optimizer runtime product. So let's talk a bit about Stream. Stream is Stream is a benchmark that measures the memory bandwidth, and it's here. Let's try to compile it and run it, okay? Fortunately, we chose something that is really short. And what we're interested in is this number, the triad. So let's run it again. So this is actually running on my laptop. So we are getting a very low result because of the video of the webinar, the video streaming. But you can see more or less the results, and you can also see the high variability here. So let's try recompiling it. Let's try another flag. Okay, suddenly we see a bit higher numbers. Let's try with -0.1. Okay, now we see significantly higher numbers. Flag mining done manually. So let's see how we can actually automate that. Okay, now I'm going to invoke Optimizer Studio. That's how it looks like. And it's now taking some samples of the baseline. Okay, so we had the first sample coming in. Okay, so let's leave that running and continue and explain a bit about what we are actually doing. So we are invoking a tool called Optimizer Studio. Optimizer Studio will pass compiler flags to a script that receives these compiler flags. It builds the stream example. It runs some kind of functional test just to see that it works and the build was successful. And then it runs a performance test. This is basically just running stream and grepping for the actual result, and then feeding this back into the tool. And the tool will continue running this flow until it reaches some kind of exit criteria. And after that, it will just output the result. Let's see if we can see something already. We're only at 3 samples. Okay, let's continue until we see something there and talk a bit about continuous optimization. So we have the commit, build, automated functional tests, and deploy type of continuous integration. So let's say somebody commits a code, it passes through build, through automated tests, and now after we know that it's a good configuration, we pass it through the continuous optimization pipe, which is basically what slide. You choose the compiler flags, you build, you run the tests, you perform the performance tests, and this is done iteratively until a set of new compiler flags are found. And once this is found, it's committed back to the pipeline, so that in this slide, the implementation is asynchronous. So the flags that are found are pushed back, and you will get these new flags in the next time that you commit a change. This, of course, is just one implementation. You can do it serially, but as a best practice, the flow of continuous optimization can run for several hours, and you would probably not want to delay the whole pipe just for the optimization part. And of course, if you see that the optimization got real great results, then you can decide to build, you can decide to invoke another build to get the new settings. So one moment. It's just
would you like me to share my screen? It works on. Maybe your Windows is having issues running the streaming right now.
Yeah, it's making everything run slower. No, I prefer not to, because I'm afraid it will just it crashed my computer when I disabled the sharing. So okay, so that is Tomer Paz, our VP of product. So let's try to do the continuous optimization part. So I'm going to push a change repository. Okay, so I pushed a I pushed a change to the remote repository, and now this remote repository on GitHub is connected to Jenkins. And since we have polling going on, but since this is a demo, I will just invoke it manually to save time. So now we have another task in Jenkins, which is in charge of the continuous integration pipe here. Okay, we can see it restarting now. Let's look for a moment on the configuration files. So for continuous optimization, these are basically the things that we need to define. This is just a short version of the file. So we have, we define the repository where we can get the files and the branch. Max cycle time means how much we are willing to invest in each cycle of continuous optimization. So for this demo, we put it on 2 minutes, but obviously for larger programs and larger installations, then you might say, I want to invest 3 hours in continuous optimization for every commit, or for every commit that has a specific tag. The next one is when to push the results. Maybe you would not want to push new compiler flags unless they improve performance by a certain amount. In this case, we said that if the performance improves by 1%, then we push back the results. And then you have the command to compile and build the environment, and you have the command to invoke the load. And in terms of Git, you can define the flags that are used for the make and the results of the optimization in JSON format. So you have to specify these two files. In terms of the optimization, so in this case, we're using GCC 7.1. So you include these knobs, all the params, architecture, and base parameters. And some of them are excluded because it did not work on that platform. You can define that every configuration is tested 10 times. This is in order to deal with noise. Because this is a short benchmark, you have seen just running a few seconds, then it's better to run it many times in order to get more confidence from the results. We also have other mechanisms, but this is a subject for another webinar on how to deal with variability.
That's probably why it took you a long time to see the first samples, because you 10 samples each, and then you limited it to only a few minutes to run, so it didn't do so much.
Correct. I limited it to only 2 minutes.
Right. So if we reduce the number of samples, you will see results very quickly.
Great. So this job has already finished. And we can see here the output of the result. It had committed new flags, which had 174% of improvement. So let's get back to GitHub. Okay, so let's look at this commit of 175%. So basically, it populated the file called flags.make with the new flags. You can see here -03. That's what it found. And all kinds of flags that I really don't know what they do, but that's the whole idea here, that you don't have to be an expert to perform compiler flag mining. You can have the tool do this for you. And here you have the JSON format file. Okay. So the reason why I'm returning to this tab is that the way we configured it is to invoke the optimization again after every time. So now another round of optimization is taking place. And if we come back in 2 minutes, we will be able to see what has been achieved, whether we can improve performance above 11,000. That's the raw value of Triad on that server. Okay, let's continue. Here are some static results that we've achieved on that particular server. So you run it without optimization flags. That's more or less the result that you get. It's an average of 10 samples. And these are the different -0 flags. The best performing one was -0 fast. It got 175%. Then we ran it with Optimizer Studio, and we used the flags that were recommended. This particular run took 30 minutes. And after 30 minutes, we were able to achieve above 12,000, 1.6% over -0 fast. Now, this is a very, very simple program stream. We have seen in real-world cases that you can get much better performance than -0 fast in real applications. Another thing that I wanted to discuss with you is a post-processing step that we have embedded in Optimizer Studio. So when you are optimizing compiler flags, you have hundreds of flags that many of them don't have a real effect on performance, but you don't know which ones will not have an effect. And it's desirable that the list of flags that you use for compilation will be only those flags that do actually have performance, because otherwise you don't want to stray too much from the defaults. So we have a way of, with the minimal number of new measurements, to give a score for each one of the knobs. And if you order them by influence and sort, then you get this kind of graph of the effect of the knob compared with its number. And you would want to keep this part, and all of the right part you want to trim. You don't want to use it. So this is another feature that you have in an automated tool that can save a lot of time. And let's talk a bit about real-world use cases. So Marvell has published a use case with Optimizer Studio, where they try to optimize the core mark benchmark. And they were able to achieve 10.5% of improvement using the tool. And that was particularly interesting because they achieved using manual optimization around 7%, a little above 7%. And the baseline here was -0 fast. So above -0 fast, the experts were able to achieve around 7%, and the tool was able to achieve around 10%. And this was done in 3 hours of running the tool. And that was with a previous version of our software. Now it will be much faster. We see this use case happening in a lot of industries, a lot in financial institutions where latency is key, especially in use cases of high frequency trading when you need to lower the latency. We see this in semiconductor companies, telecom companies, cloud customers, and more. And what we typically see is that you get, the bottom line is we see between 5 to 20% of improvement when you start experimenting with compiler flags over -0 fast. And because this can be integrated into an existing CI flow, you get it basically for free. You implement it, it takes you 1 day, and it works in the background. Sorry about that. And the idea is that compiler flags are just the beginning. So one way is to optimize the compiler flags, but what about the Nginx tunables? What about the processor tunables? What about Linux? So if you add all of those to the mix, you can get much better performance. So that sums it up, and I'll be happy to take questions. I'll just add that the second attempt to improve performance has only gotten 0.6%. So it was less than our 1% threshold. So we did not commit the new flags. So, Tomer, are you there? And Steve?
I'm here.
Okay. Okay, great. Because I cannot see the questions. Are there any questions?
Yeah, I already answered some. More coming in now.
If it's something that is relevant, maybe you can explain.
Yeah, so maybe if you want to answer about how do I see Simon Raviv asking a question, how do you deal with kernel boot parameters optimization which require reboot?
So that's a good question. The way to do it is to have 2 machines. one of them running the optimization process, and one of them having it's actually the device under test. And you define the tunables in the first machine, and you apply them in the second, and measure it on the second. We have users doing that to optimize BIOS settings.
Another two questions, one by one. I'm starting with Andre Bondi. Suppose you have a program that has a CPU-bound and I/O-bound phases. Can your tool vary the amount of CPU and the amount of I/O so that you can have flag combinations for different mixes?
Yeah. So in static optimization, you optimize for the average phase. But in dynamic optimization, where you have the agent, it can react in real time according to the needs of different phases. But I didn't talk about this a lot in this webinar. That's for another webinar.
Another question from Adrian Ilay. In order for Consortia to gain confidence in results from noisy workload, is there a way to run on multiple machines in parallel to save time? Actually, it's a feature.
Yeah, it's what?
It's a feature. You can talk about the feature.
Yeah, the feature is parallel optimization. So basically, you can parallelize the tests to save time, and it basically scales with the number of servers that you use.
Yeah. Bear in mind about the difference between the nodes that you're running the load on, because that might add a new dimension of variability as well. So you need to take that into consideration. Let's see, there is another one. Deepak Dogra asks, maybe I can answer that. Can we utilize this tool for .NET and Java application builds? Absolutely, yes. Here in the demo, we just shown how to play with flags of GCC, but we can actually utilize the tool not just for the build, but for Java applications in runtime, playing with the knobs of Java options, for example. And for .NET, we haven't prepared yet, but we can do that if there is a demand for that. Also optimization flags for compiling.
But we have done .NET optimization.
Yeah, for the application, but we don't have embedded knobs for compilation right at the moment. For compilation flags, we currently have GCC, various versions. I hope we answer to the questions well. Simon again. Which compilers do you support besides GCC? Well, I just said currently just GCC. We are thinking about adding also LLVM. It's probably easy to do, and perhaps .NET in the near future.
Yeah, and Intel compiler, of course.
Yeah. And by the way, if you have any interest in any kind of compiler and you want to share with us or want us to help you with that, then talk and we can do that. It's just a matter of defining them as parameters in the knobs YAML file that you saw earlier. There's another question. Adrian Ile again. Let's suppose I want different flags for different source files, and the performance of one file may affect the others. Is there a way for Consortia to optimize this? One set of flags for one file and a different for another, but using one combined result to optimize with.
Yeah, so this is something that is inherent to the tool. So you can add any tunables in any part of the system, and it will tune the system as a whole. So we have great examples where we show how we tune the Linux OS and the processor and the application, everything together. And then when you see the results, you see tunables from all around the system, which is something that is very difficult for a human to do, but it's trivial for a tool because the tool does not care where your tunables reside. It just cares about the result. This is what is called black box optimization. So you don't really, the tool doesn't really care what's inside the black box. It only cares about what tunables it can feed to the box and the result that is out from the box.
Just a second. I took a screenshot just in case you want to share command-line results for the stream experiment. Just a second, let's see more questions. There is one. Jasper Francis, any feature for garbage collection while running the optimization? Yeah, if you're not talking about compilation flag or runtime flag, that's a question to Jasper. In runtime for Java, we have garbage collection flags.
All the -XMM parameters.
Yeah, that's about garbage. That's the other option, the other knobs, but specifically for garbage collection, there are also many knobs. About 10 of them, I think. We have an example, by the way, in Optimizer Studio. If you install the package and cd to the examples folder, you can see many examples, including nginx, Postgres, MySQL, and Java performance benchmark as well, running some JRE benchmark that show how it optimizes with the flags. Runtime flags. Yeah, that's more or less a summary of the list. Now you can see. Oh, it's too dark. Any more questions?
Okay, so I think we can wrap it up. 45 minutes to the point. So thank you so
any
much.
Final word, maybe any final word from Steve?
I guess my comment would be, I wish I had this 15 years ago. It would have made our systems analysts a lot more productive, and ultimately it would have made the customers a lot more productive. And you know, as I'm watching this, in my mind, I'm going, God, I wish I could take this, integrate it with some stuff I'm not going to talk about, and do something that would be real significant step forward.
Okay,
great. So thank you so much for Steve for joining and being a guest speaker at this webinar. Thank you everybody for joining. Thank you, Tomer, for running this and doing all the experiments. And that's it. I hope to see you soon. Speak with you soon.